Hello, everyone. My name is Michael Valley, and on behalf of the Applied Technology Council, I'd like to welcome you to this webinar on nonlinear analysis recommendations in FEMA P-2208, NEHRP recommended revisions to ASCE 4117. This webinar is brought to you by the Applied Technology Council under a FEMA NEHRP Architect Engineer contract. This is the first of 3 webinars on FEMA P-2208. Webinars addressing recommendations for unreinforced masonry and for concrete structural walls will be released in the coming months. If you haven't already, you can download the handouts for today's webinar using the link in the chat. We know that many of you are interested in receiving professional development hours for your attendance today. For those who registered and attend the webinar, a certificate documenting professional development hours will be sent by email within 4 weeks. If at any time during the webinar you have questions, please type them in the Q&A window that you can open from the Zoom control panel. We're planning to have a live question and answer session at the end of the webinar, so please submit your questions as you have them, rather than waiting until the end to submit them. We'll answer as many questions as we can, time permitting, at the end of the webinar. If there are questions that we're not able to answer live, we plan to provide written responses for as many as practically feasible. I'd now like to turn it over to Christina Aronson from FEMA's Earthquake and Wind Programs branch. She'll provide a brief introduction to today's webinar. Christina, please go ahead.
Thanks, Mike. Hello, my name's Christina Aronson, and I'm a structural engineer at the Federal Emergency Management Agency's National Earthquake Hazard Reduction Program, FEMA NEHRP. It's my pleasure to welcome you today for the first of the 3 webinars covering the NEHRP recommended revisions to ASCE 4117, and which is the document FEMA 2208. Today we'll be covering the background and studies of the P-2208's recommended revisions to nonlinear analysis portions of the ASCE 41. Just to set the stage, FEMA has the goal of reducing the ever-increasing costs that disasters afflict on our country. Addressing the risk presented by our population of existing buildings, of course, is the most effective way of reducing the cost of future disasters. NEHRP is composed of 4 agencies: NIST, National Institute of Standards Technology; USGS, US Geological Society; National Science Foundation, NSF, and FEMA. As part of FEMA's statutory responsibilities under NEHRP, FEMA is charged with supporting the investigation of seismic technical design issues, the development, publication, and dissemination of technical design documents and construction guidance products, and support of model codes that are cost-effective and affordable. This report documents the work of a 5-year FEMA NEHRP project. FEMA submitted 35 detailed proposals, revisions into the official ASCE 41 consensus standard process. FEMA P-2208 presents the submitted change proposals and commentary in addition to the results from the technical studies that inform the proposals. It's not intended to replace ASCE 41. FEMA values the partnership with ASCE and the important work it does with the national consensus standards for buildings. We hope you'll find this webinar useful, and we encourage you to let us know if you have any questions. We also want to thank Applied Technology Council for managing this project and helping deliver this session under the FEMA NEHRP Architect Engineer contract. Additionally, we thank Bob Pekelnicki for presenting here. He is truly an encyclopedia of this information. The other names and affiliations of all who contributed to this work are provided within the report itself. Without their dedication and hard work, this publication would not have been possible. The nation is safer from the next earthquake as a result. So with that, back to you, Mike.
Thank you, Christina. Now let me tell you just a little bit about our presenter today. Our presenter, Bob Pekelnicki, is a senior principal at Degenkolb Engineers. For over 20 years, Bob has been active in designing, evaluating, and retrofitting buildings for earthquakes and other natural hazards. Bob is a leader in the field of earthquake engineering and devotes a lot of his time to developing better performance-based earthquake engineering methodologies, building codes, and standards. He's been a member of the ASCE 41 committee since 2009 and was chair of the committee for the 2017 and 2023 editions of the standard. He was a member of the Project Technical Committee for the development of FEMA P-2208 that we'll hear about today. Bob, it's up to you now.
Thank you, Mike, and thank you, Christina, and welcome everyone. Thank you for taking time out of your day. I know everyone is probably very busy, and hopefully this webinar will be a informative and useful contribution to your knowledge base on seismic evaluation and retrofit of existing buildings. So today I'm specifically going to be talking about the changes that were made to the nonlinear analysis provisions in ASCE 4123. As Christina said, we'll be talking primarily about the changes as they were proposed by the FEMA P-2208 or the ATC 140 project that is memorialized in FEMA P-2208. So one of the things that FEMA chose to do, which as the chair of the committee I was eternally grateful for, was to fund applied research to tackle challenges that volunteer professional committees do not have the bandwidth to undertake. So as I think many people know, ASCE 41 is a volunteer effort done under the banner of the American Society of Civil Engineers, specifically the Structural Engineering Institute. The volunteer committee does vet all of the proposed changes to the standard, and through the ASCE consensus process, that is how the standard gets updated from 4117 to 4123. So the ATC 140 project that led to FEMA P-2208 went through and performed a lot of research and did a lot of great work that developed change proposals that were then handed over to the ASCE Standards Committee. And so the purpose of this webinar is to discuss all of those changes and specifically the research that went into those changes that led to changes in the nonlinear analysis sections of the document. The ATC 140 project broke into 4 or 6 working groups, as you can see here, and generated 35 change proposals that all went to ASCE 41. As Mike said, there will be webinars on the nonlinear analyses, the concrete structural wall changes, and the unreinforced masonry changes. The latter two will be forthcoming, so please keep an eye out for those on LinkedIn and in your inbox. So this is showing you the first 5 pages of the ASCE 41 standard, where they summarize all the changes that were made. And everything that's highlighted is a change that started in and can be found in FEMA P-2208. So you can see that about half of the significant technical changes that were made in the standard in this cycle were done and originated in the ATC 140 project. And as we go through and talk about things today, we want to make a note that today's webinar is really focused on the applied research and the initial recommended change proposals. Because ASCE 41 is a consensus-based process, once those change proposals were handed over to the ASCE 41 Standards Committee, the Standards Committee was fully within their bounds to make modifications to the changes proposed through this process. And in most cases, they did. If you're interested in what ended up in the final document, ASCE is hosting a series of webinars on the specific changes that are in ASCE 4123. So the intent of this webinar is to complement a webinar that was previously given a couple weeks ago and can be reviewed, and the recording of which can be purchased and viewed through the ASCE Continuing Education webpage. So if you're interested in the specific changes in the document, I would recommend you also go to that. But for the background and the initial proposed changes, you're going to find that out today. Additionally, FEMA is hard at work producing an update to FEMA P-2006, which I think many of you probably use on a regular basis as the design examples. That document was design examples to ASCE 4113, and we're going to jump over 4117 and go right to updated design examples for 4123. So look for that in late 2025. So with that, we're going to move into the nonlinear analysis changes. But I would be sorely remiss if I did not first acknowledge the specific contributions of the Nonlinear Analysis Working Group. These people did a lot of work and thought leadership and guidance and criticism that led to the initial changes that we proposed to the ASCE 41 committee. So I'll save reading everyone's name, but please take a moment to look at these and recognize that these people all made significant contributions that had they not been involved, we would not have gotten to where we got with this process. So the first question that jumps out is, why update the nonlinear analysis procedures in ASCE 4117? They're being used and they seem to be being used successfully. The issue at hand is that many of the provisions in ASCE 41 date back to the nonlinear provisions in ASCE 41, or I'm sorry, FEMA 273, the initial FEMA funded guideline document that eventually evolved into ASCE 41 as it is today. When those recommendations were developed for nonlinear analyses, this was in the mid-1990s when nonlinear response history analyses was a thing of research. And even when it was a thing of research, it was a very idealized and scaled down version to then what people do today. So 25 years ago, most people were performing pushover in design offices if they were doing nonlinear analyses. There have been a lot of hardware and software improvements in the past 25 years, which have made nonlinear response history analyses, I think, the go-to for at least myself and many of my colleagues in doing evaluation and retrofit of existing buildings. And there are two projects that I think really help push this forward. The first was another ATC project that was funded by NIST, the ATC 114 effort that led to the publications NIST GCR 17917-45 and then -46 volumes 1 through 3. And those were recommended modeling parameters and acceptance criteria for nonlinear analysis for evaluation, retrofit, and design. And then specific one for steel buildings, a specific one for concrete buildings, and a general document on nonlinear analyses. So these are great documents to go into your favorite search engine and punch in and download. They're free through NIST's NEHRP website clearinghouse. The other great work was done with the Tall Buildings Initiative for guidelines to performance-based seismic design of tall buildings. Starting about 20 years ago, engineers started doing nonlinear response history analyses to design tall buildings, recognizing the benefits in being able to do structural systems that were slightly not in conformance with ASCE 7, but could produce the same reliability of resisting collapse in a maximum considered earthquake. And so through the 20 plus years of use of this, these projects really synthesized the material and provided good basis, and in many cases filled in gaps that are in the ASCE 4117 provisions for nonlinear analyses. So as we embarked upon the updates, one of the things that we felt would be really important to do is to make sure that every change we proposed was vetted through real archetype buildings. And this is also important because the goal of producing changes to the standard is to improve upon the standard. And we wanted to make sure that any changes that we proposed did not have unintended consequences that you really only see when you get into doing real projects with real buildings. So what we chose to do was take on a 4-story steel brace frame building that was slightly irregular in plan, and a 4-story steel moment frame building that was also was more regular in plan than the steel brace frame building, and vet all of these changes through these archetype buildings. So you may be wondering why you don't see a concrete building there. And that's not to say that we didn't look at a concrete building, but we really focused the concrete building on the concrete structural wall changes that will be presented in a future ATC webinar. So we want to start the stage with some significant updates to the modeling parameters and acceptance criteria for nonlinear analyses. If you go back historically to FEMA 273, they proposed what was known as a second cycle backbone curve, where you would take a hysteresis from a research testing of a structural component, where they isolated one specific component action and did cyclic testing on it and generated the component backbone, or I'm sorry, the component hysteretic curve, And then you drew a backbone through, as you could see, the second cycle. And this was intended for pushover analyses, that if you use this backbone curve in a nonlinear static pushover, it would produce a reasonable representation of the display shape of the building at the maximum response in a actual earthquake or a nonlinear response history analyses. It was started to recognize as FEMA 273 was used over the years that this second cycle approximation was conservative. And so in the supplement 1 to ASCE 4106 in the late 2000s, there was a change made to work on first cycle envelope, or just an overall envelope of the hysteretic curve. That would define your nonlinear backbone curve. So recommendations were made and changed in ASCE 41. One of the challenges is that the question is, where would you find this? And I think many people did not know that there is section 7.6 for alternative modeling parameters and acceptance criteria that set forth the procedure which you would take hysteretic testing and go in and create a nonlinear backbone curve. But the way that this section was written, the black and white of the standard would say that this is for project specific testing. It is not for generalized component testing. And you need 3 tests. You can use different loading protocols. You can even use one monotonic loading protocol. You do a first cycle envelope, and then you classify the elements as either type 1, 2, or 3, with type 1 being deemed deformation controlled, type 2 being a little gray, whether you can call it deformation controlled or not, and then type 3 being deemed force controlled. And so the challenges that we were facing as a team was, how do we write rules for not just project specific testing, but general modeling parameters and acceptance criteria? Because also happening in the ASCE 41 update arena was the desire by the American Concrete Institute and the American Institute of Steel Construction to take ownership of the reinforced concrete and structural steel chapters. And so if other organizations were going to be developing modeling parameters and acceptance criteria for ASCE 41, there was a desire to have a standard way to develop it, not just on a project specific basis, but on a generalized basis that would be put into the standard. And as I said before, the NIST GCR 17917-45, or the ATC 114 project, spent a lot of time thinking through how you could do this and how you could write rules for developing generalized modeling parameters and acceptance criteria, and also proposed updates to many of these modeling parameters and acceptance criteria. Because one of the things that is maybe not known is that a lot of the modeling parameters and acceptance criteria are unchanged from FEMA 273, which means they haven't even been updated to go from a second cycle to a first cycle envelope, let alone be updated with 25 years of additional component testing and research. So one of the things that came about in the ATC 114 project was the recognition that loading protocol matters for developing modeling parameters and acceptance criteria. And heretofore, there were really only the 2 done of symmetric cyclic, which is the fully reversed cyclic loading protocol. That's been kind of what I feel is the standard loading protocol used to test components for cyclic response that would be simulated by earthquakes, or a monotonic curve where you just simply push on the component to see how it deforms. And as you can see, looking at the red and blue curves on the left figure, it's a very different representation. And people have started theorizing and coming up with different collapse protocols, or loading protocols that would simulate collapse in a building, which in an earthquake is often a consequence of a strong initial pulse and then cycling in a deformed shape that is not symmetric. So the ATC 14 project created they didn't make a specific recommendation about the use of loading protocols, other than to provide caution about using monotonic loading protocols because they can overpredict the deformation of the components. And as you can see on the figure on the right, They even provided some conversion factors between monotonic to a cyclic backbone curve. So where we ended up with the recommending for the ATC 114 project was to adopt some of their recommendations that would, in some cases, change the modeling parameters and acceptance criteria. Shown here is a backbone curve for a structural steel pre-Northridge moment frame beam column connection. And as you can see, the loading protocol is reduced a little bit in the major deformation controlled arena, but has longer residual strength, and then has potentially new acceptance criteria also. So that was one of the things that was discussed, but also seeing how, if you go back to these slides, you can see that one test does not necessarily give you the exact answer. And when you do multiple tests, you're going to get multiple different answers. So each of these parameters on the backbone curve has a statistical distribution. And one of the things that we were debating is what should we use when developing a nonlinear response history model? Should we use the mean or median of the modeling parameters, or should we use something higher or lower? And so one of the things that we decided to do to understand the response of, or the sensitivity of nonlinear analysis models to the choice of the backbone curve in the modeling parameter was to do some Monte Carlo simulations where we built the model using only median properties, and then also built the model with backbone curves that were based on a 10th percentile and a 90th percentile of the modeling parameters, and ran the nonlinear response history analyses to see what the spread would be. And as you could see, there's obviously an extreme spread. If you go to the 10th percentile of the modeling parameters, you're going to, and this is for the four-story steel moment frame building, you're going to get a wide swath of response. Versus if you went to the 90th percentile, you're going to get a much lower drift response than the model that was done with median parameters. Then we turned around and we did a Monte Carlo simulation of the building's response where each point on the modeling parameter and acceptance criteria curve for every nonlinear hinge in the building was varied based on the statistical distribution recommended in the ATC 114 series of reports. And what we found there when doing the Monte Carlo simulation of that was that the median of the Monte Carlo simulation was not too far off from the median or the analysis model that had all median parameters imported into it. And so this gave us confidence that if we were going to recommend how you would develop modeling parameters for ASCE 41, and also in some respects revalidate the direction of building a model that is based on modeling parameters that are all at the median response of your test data, you would be getting a somewhat accurate response representation of the building's probable response under an earthquake. So this gave us confidence to say that when you construct this backbone curve, each point on this backbone curve should be taken as a median of all your test data normalized. And so we didn't deviate too much from the standard backbone curve envelope shape that you're probably very familiar with in ASCE 41. And really the biggest change we did is we introduced a new point, which is here, point F. And point F is identified as the point called loss of vertical load carrying capacity. And the purpose of point F is the recognition that in many component actions, there is a difference between the damage state where the component loses the ability to resist lateral forces, but it still has enough integrity to support the gravity loads tributary to that component. And so it could be pushed further before it truly fails. And so the idea being is you could build a nonlinear response history analysis model and let your, if your software was capable of processing the transition from point E to point F, you can allow your analyses to continue beyond point E, and you would pick up unacceptable responses through global instabilities, but you may notice that you can still, because there's enough other components that have not passed point E, the global model can still respond, but it's not until you hit point F where partial collapse may occur. And as we're targeting the collapse prevention performance level, that's really important. And so the idea here is to build this, and we did not populate point F in the modeling parameter and acceptance criteria tables in the standard because that just doesn't exist right now. Very, very few researchers push their tests beyond point E. And I would argue most researchers don't even push their tests to the true point E deformation, let alone going all the way to point F. I mean, the closer you get to these loss of lateral force resistance and especially loss of vertical load carrying capacity, the more likelihood you are to damage your testing equipment or create safety hazards within the research lab. So our goal with introducing these points was to hopefully set the stage so over the next 10, 20 years, researchers can develop new ways to do these tests that push their components there and extend out the deformations and get more accurate modeling parameters and acceptance criteria. Because I think one of the whole overarching reasons for having ASCE 41 and continuing to update ASCE 41 is the recognition that seismic evaluation and retrofit of existing buildings is essential to our community's resilience. And what is just as essential is being able to separate buildings that are just not as good as a new building from buildings that are truly dangerous. And so if every building fails the standard, then it's hard to really separate just not good from dangerous. And so one way to do that is to have more accurate models, or at least models that are closer to predicting collapse than the previous models do. The other thing that's really important in a nonlinear response history analyses is making sure that your constitutive model behaves appropriately. And heretofore, ASCE 41 has been concentrated on creating a backbone curve that populates what is happening in quadrants 1 and 3 of the full hysteretic response of the components. But the standard says nothing about or gives no guidance other than to say match testing for what quadrants 2 and 4 should look like. And so another change, which was done as a change in this general section, which we hope is setting the stage for new columns in the modeling parameter and acceptance criteria table in future editions of the standard, to talk about the level of hysteretic pinching that would occur. And we created 4 different categories, and the idea being that eventually you'd have one of these 4 listed in the next to the modeling parameter in the tables in ASCE 41, AISC 342, and ACI 369.1. So this can give some general direction on this to make sure that people are using models. And when you're doing a quality control check, whether internally or through an external peer review, that you can look at your force displacement hysteretic shapes and determine if your models are behaving as they should be based on the envelope in the first and third quadrants, and also what the hysteretic shape looks like in the second and fourth quadrants. And it's really based on the percentage ratio between the enveloped hysteretic curve and a perfect elastic plastic hysteretic curve. So we also then revisited the acceptance criteria in ASCE 4123. So one of the things that, if you think about it, previously we set 4 nonlinear analyses. We set the collapse prevention point as point E or some fraction of point E. And then all the other modeling parameters kind of flowed from that point, except the immediate occupancy modeling parameter, which flowed from point C here, the transition from strain hardening to strength degrading. So recognizing that loss of lateral strength isn't necessarily what's going to define collapse prevention and therefore also life safety, which is taken as a margin of safety against collapse, but it's loss of vertical load carrying capacity. So we have our unacceptable response checks to make sure that there's not a global collapse, But then from a local collapse standpoint, we really care about setting our collapse prevention at the loss of vertical load carrying capacity. So there's now provisions in there that if you have enough test data, you can set your modeling parameter, your collapse prevention acceptance criteria at a multiple of the loss of vertical load carrying capacity. I believe it's the 25th percentile on a statistical distribution of point F. If point F is the median, that relates to about a 70% of the median, depending on the coefficient of variation of your test data. Now, obviously, that's not going to be done because, as I said before, most things don't have this, but we're setting the stage for this. So we still retain the ability to set it the old way that you set it at point E and march back. But I want to draw your attention to one very significant change in ASCE 4123's modeling parameter for nonlinear analyses, and that is setting damage control explicitly at point C, as opposed to setting it as a halfway point between the immediate occupancy and the life safety performance level. And the reason for that and the motivation for that came from some regulators who were looking at people proposing project-specific testing where they had a very large deformation on pre-Northridge moment frame connections before the connection fully lost all lateral load resistance, going out to a rotation of 0.06 radians. But the flange welds were fracturing at around 0.15 radians. So the median of that would put you around 0.03 for your damage control point. But this would mean that half of all your moment connections in the building might be fractured. That's not necessarily appropriate for damage control. And so the committee debated this a lot and felt like that transition from strain hardened response to degraded response is really when bad things are happening and damage is switching from stuff that can be easily repaired to stuff that requires significant repair. Certainly not in the definition of damage control. So the idea was to limit the deformations in component actions to the transition point between strain hardened and strength degraded to limit the damage. And so damage control is now explicitly called out as being point C on the force displacement curve. So you won't find this in the tables in ASCE 41. The committee did not, and the ACI 369 and AISC 342 committees did not make those adjustments to their tables, but there is text in the standard that tells you that you need to set damage control at this point where the little red cursor is shown right now. Other changes to how you develop modeling parameters and acceptance criteria, we created an ability to bin your components as either your component actions as either critical and ordinary. We already do this in the non-structural arena, but we wanted to be able to make sure that people could do so in the deformation controlled arena also. And the reason for this is giving us the ability to then have ordinary actions or non-critical actions be have no need to check local collapse prevention acceptance criteria and really rely only on the global metric of unacceptable response, which is a better indicator of global collapse. We also relaxed what could be deemed force controlled. So heretofore, you could potentially have to define type 2 curves as force controlled actions, especially if this branch wasn't that big. And so what we've done instead is said to be a force controlled action, it truly needs to look like a type 3 curve where you come up and you immediately start to degrade, and you degrade to a very low strength, almost zero. If you come up, you break, and you degrade to some residual strength, that can be considered deformation controlled, even though it may look, the first part of the force displacement curve may look like a type 3 curve. So to summarize, we now have we recommended a new section on aggregating testing development for general use modeling parameters. And I should also note that every one of the recommendations that ATC 140 sent to the ASCE 41 committee, while they may have been adjusted or altered slightly, they were all accepted by the ASCE 41 committee. So these changes in some form are in ASCE 41. We do not permit the inclusion of monotonic testing or we recommended not permitting monotonic testing for developing backbone curves because it's so much more robust than cyclic testing would show. We added a loss of vertical load carrying capacity to the backbone curve, identified 4 default hysteretic shapes. We're permitting statistics to develop your life safety and collapse prevention performance levels, setting damage control specifically at the point where you switch from strain hardening to strength degrading, eliminating local acceptance criteria checks for deformation controlled actions that are ordinary for collapse prevention, and then when you can consider something force controlled. So this is a real big change, but it doesn't necessarily have big changes in the short term because this didn't result in a lot of changes. Some of the modeling parameters in AISC 341 and ACI 369 and the new concrete wall modeling parameters, which ATC will be providing a separate webinar for, did take a lot of these recommendations into account when developing their modeling parameters and acceptance criteria. But a whole bunch of other parameters in the standard have not benefited from a relook based on these new provisions. And we're hoping in future cycles of the standard, they will be, and that you'll see continued adoption, improvement of the modeling parameters that are recommended in the standard. So now to move on to another topic, which has been commonly used, but didn't have as many regulations and, as some would say, guardrails on it. And that's the use of fiber models in nonlinear response history analyses. And for those who are unfamiliar with these, all the modeling parameters in ASCE 41 are the points that create the backbone curve and even the hysteretic shapes are recommended for lump plasticity nonlinear springs at the ends or midpoint or wherever on a member. But there is an ability to use a different type of model that discretizes the cross section into individual fibers, and each individual fiber has its own stress-strain relationship that then is tracked directly in the analysis model and leads to the nonlinear behavior of the component. And so this can be used for concrete, is very commonly used for concrete, especially concrete walls. It can even be used for pre-Northridge steel moment frames. And if you look at NIST GCR 17917-46B, you'll see an appendix that talks about using fiber models for modeling weld fracture. And NIST 917 or GCR 17917-45 talks about even using fiber models to represent brace buckling. One of the things, though, with the use of fiber models is the transition from the stress-strain response to the component action response. And heretofore, there were not really any directions on what you needed to do or what level of validation was needed. So because most researchers test components, they don't, when they test the components, they're not tracking the strains in discretized fibers. They're just generally tracking a moment rotation or shear deformation, shear versus shear deformation. So, and those are what the backbone curves in ASCE 41 are based on, or what the hysteretic shapes in research reports are based on. And so we recommended that the provisions say if someone chooses to employ fiber models, they have to provide some level of calibration back to either research testing or the backbone curves identified in the standard or standards referenced therein, like AISC 342 or ACI 369. And they also have to match the hysteretic shape, not just match the quadrant 1 and quadrant 3 force displacement relationships. So we're setting a higher bar for force controlled elements and saying that the acceptance criteria should be based on the backbone curves or derived from backbone curves in research testing. So we're steering people away from using usable strain limits as the acceptance criteria for fiber models. And the reason for that, there's a really good discussion of that in that NIST GCR 917-45 in the concrete wall chapter. of how it's very hard to determine usable strain limits, and usable strain limits can often be very sensitive to gauge length, much more so than just if you were to put down rotation gauges and track moment rotation to determine your modeling parameters and acceptance criteria as opposed to usable strain limits. So to summarize where we ended up with fiber models is we definitely want to allow them and encourage their use because they can, in my experience, do a much better job of predicting hysteretic response of components than lump plasticity models can. But it's essential that they're calibrated and that the acceptance criteria is aligned with the behavior, and it's not just based on generic usable strain limits. So as I've been talking about, you've heard me using the term critical and ordinary actions. And, one of the challenges that we found was in the ASCE 4117 standard, when we introduced the concept of critical and ordinary actions for force-controlled elements, and even non-critical, we actually didn't define them other than defining critical action in the definitions. But we had some commentary talking about ordinary and non-critical, but we didn't have an actual definition in the provisions. And as you see here, they were only used for force-controlled actions, and ordinary and non-critical didn't have any difference in their acceptance criteria. So for critical actions, we amplified the force-controlled action demand on them to provide a higher reliability that those actions wouldn't fail in the analyses. So we made some changes. We, as I said, had no difference between ordinary and non-critical. And we also recognize that deformation-controlled actions can be critical too. Flexure in a column, which is a deformation-controlled action, there's a point at which you have so much flexure in that column that column loses its ability to support gravity load. And if that column is on the first floor, you can bet that that's a critical element, and therefore that flexure is a critical action. And we didn't differentiate between the flexure in a column and the flexure in a beam in our modeling parameters and acceptance criteria. So we made a change to explicitly define critical actions in the standard, setting them as you see here, recommended that it's the failure that result in the collapse of more than one structural bay or a significant reduction in the strength of the lateral force resisting system that resulted in a weak story or torsional strength irregularity per section 7311 of ASCE 41. So it was also a recognition that if that action lost its ability to either exist in the case of a force-controlled action or if it lost its ability to support lateral load in a deformation-controlled action, and it significantly changed the response of the building, that was a critical action. And then there should be different acceptance criteria for critical actions than ordinary or non-critical actions. So that moves us to changes we recommended for force-controlled actions. So for those who need a refresher, there's the deformation-controlled actions of tension brace yielding or compression brace buckling, and then there's the force-controlled action of the brace fracturing. And so when you do a nonlinear analysis, you put in hinges to represent the response of the deformation-controlled actions. But you generally, or at least I generally, do not put in hinges that would represent the failure of the deformation control or the force controlled actions. And so in your nonlinear analysis model, you may be overstressing force controlled actions. And heretofore, we were then taking that in a post-processing manner and checking it to say, is the action, did the force controlled action overstress or not? And if it did, we say that, well, the building didn't meet the performance objective. If it did not on the mean or the amplified mean, then that was okay. The issue at hand, however, is everything in the analysis response after that force controlled action is overstressed in each record is not an accurate representation of the building's response. And so we took the brace frame model, archetype model, and we modeled it on the left as people normally do, modeling just the tension brace yielding and the compression brace buckling. And then we developed another model in which we set up for the connections to fracture. And that if the connections fractured, they then lost the ability to support seismic load. And you can see there's a significant change in the response of the structure for the model where the not force controlled actions were explicitly modeled, which is permitted in ASCE 41. And you would get a different response of the building. And so there's a lot of discussion about within the project about, you know, is this important? And to the point where should this be a unacceptable response if you overstress these elements, even if they're ordinary elements, because a brace connection is defined as an ordinary element. The failure of a brace connection does not lead to immediate loss of gravity load support for the brace frames, or you would hope that it does not. So the committee or the team spent some time discussing and provided some recommendations that says, first, all actions not explicitly modeled in the nonlinear model with a force deformation curve must be considered force controlled. And if any of those force controlled actions, whether they be critical or ordinary, are overstressed in the model, that is an unacceptable response. So now a new unacceptable response check is saying you have to go in and you have to check the forces in all force controlled actions. Now you get to check them against the median or expected properties as opposed to the lower bound for this unacceptable response check. But what we're trying to get at here is to say, if your model shows response after force controlled actions are overstressed, your model is not valid for being added to the suite of records that's trying to produce median or mean responses. Because the whole goal of running a suite of 11 records is to establish an understanding of the performance of the building under various earthquake scenarios and a reliable mean. And if you have models or specific analysis runs that are producing results that are not true to reality, or true to reality in this sense of doing our best to develop an analysis model, because I think most people would say most of our analysis models are not true to reality, that you shouldn't contribute that record to the suite mean. And as we're talking about unacceptable response, one of the things that the committee started debating about is with the use of unacceptable response and the check on the maximum as opposed, or the 9th or the 10th worst out of 11th, as opposed to the maximum or the just checking the median, is that you're at its core, ASCE 41 is trying to get you to target a 90% reliability, that when you say this building meets collapse prevention, there's only a 10% chance that you're wrong and that the building would meet collapse prevention under the earthquake shaking you're considering. This aligns with the stated reliability for risk category 1 and 2 buildings in the maximum considered earthquake in ASCE 7. But what we found is for life safety, which is supposed to be a margin of safety against collapse, therefore meaning a higher reliability than 90% or a lower probability of collapse than 10%, if we wanted to achieve that lower reliability, we may not be allowed to have an unacceptable response in the suite of 11 records, because having an unacceptable response indicates that there's a potential that that record is producing a collapse response, and that would be unacceptable. 1 out of 11 would produce an unacceptable reliability for life safety. It would be okay for collapse prevention, but not for life safety. So after some deliberation and looking at, how particularly existing buildings that have a more vertical fragility because of their brittle behavior, saying that if you were trying to provide a 4/3 margin of safety against collapse, meaning that if you met collapse prevention and an acceleration of 1.3, you're looking at meeting life safety at a margin of safety of or a spectral acceleration of 1, you're looking at having less than a 5% probability of collapse. And so that definitely warrants not having an unacceptable response for life safety. So the committee changed the provisions to say that you're only permitted one unacceptable response in your suite of 11 for limited safety and collapse prevention. And we also did add some clarifying, or recommended some clarifying language on when you need to use 120% of the median as opposed to the mean value of the records remaining in the suite. Another thing that came up in discussions about unacceptable response, especially in the context of the collapse prevention performance criteria, is whether or not there was a drift that would be so large that there was some skepticism in whether the analytical program and the analytical model can properly capture stability and large deformations in the structural response. And so the committee spent a lot of time talking about this and sharing their experience with various different types of software, and chose to set 6% as a limit on unacceptable response. And that's a recommendation. There's some language in the commentary that talked about how you may be able to be stable at drifts larger than 6%, and that would be on the professional to justify to their peer reviewer. But there was a consensus recommendation which was sent over to ASCE 7 that 6% should be a metric used as an unacceptable response. And this also parallels a change that was made in ASCE 722, which now states that unacceptable response is defined as 150% of your peak or your mean drift that you're supposed to hold the structure to. And so then we started getting into another thing that's a really interesting component of the structure and the provisions, which is when do you model secondary components? So if you see here, this is that 4-story moment frame archetype. The steel moment frame members are the primary components. And then all of the frames that are created by the connection of the gravity framing girders and even the gravity framing beams to the columns create partially restrained moment frames due to either bolt coupling in the shear tabs or coupling between the composite slab and the shear tab. And so there is some moment resistance in this, in that connection. And so therefore these frames can be considered secondary components. Now ASCE 4117 always had the ability and required you to check and make sure that the secondary components, if modeled, were not did not have a contribution of more than 20% to the strength and stiffness of the primary components. And it even had some requirements of the strength and stiffness of non-structural components and when those should be considered primary structural components. But more importantly, I want to draw your attention to the first paragraph in this section cited that said that nonlinear models should include the strength and stiffness degradation of primary and secondary components. Meaning, in this building right here, your model is not just these red frames. Your nonlinear analysis model should include all of these green frames in addition to the red frames. And polling the project team members, it was found that many project team members do not model the green frames. And they find that it is added work, that adds to the computational time to do so for not much benefit. And then there were others who said, yes, but that may be for steel, but for concrete, it certainly matters. And deformation compatibility is really important. And that's why we tell people to do this. So the team spent a fair amount of time discussing what could we do to better align the standard with what people are doing and also produce a standard that makes people want to do nonlinear analyses and not have unnecessary burdens on doing something that can produce a better representation of the structure's response. And so we took our archetype models again, and we looked at how does the model differ when you include the secondary frames versus if you were to just model the primary frames. And so as you see there, the solid lines are a nonlinear response history analysis to different shaking, mean response to different shaking intensities of a model with just the moment frames. And then the dashed lines are the response to the building with the secondary frames included. And in this case, for structural steel building, we found that you get a benefit to adding in the secondary frames. And so you get less drift. But that's not to say that if you did a deformation compatibility assessment of the secondary frames outside of the model, using the drift that you got from your nonlinear analyses, that wouldn't be okay to determining whether or not there were concerns with deformation compatibility failures of the gravity load supporting system. And so there was a desire to move toward saying you don't necessarily have to model all of these things, and we would recommend model them when they matter. And so, and that's not to say you can't, you can always model everything, but we wanted to put some bounds around when you could do a model with just the primary components. So we decided we would slightly lower how stiff secondary components had to be for them to be classified as primary components. So if the sum of all the secondary components exceeds 20% of the stiffness of the primary components, you have to reclassify some of your secondary components to primary components. In addition, we wanted to make sure that excluding secondary components didn't result in a dramatic change in the torsional response of the building. So we also put in some guardrails that said you have to make sure that excluding all of the secondary components does not result in a change in your center of rigidity by more than 10% when you take out all the secondary components. And then the last one, which is an interesting one, is that taking out the secondary components cannot decrease demand in the in the primary components. And you may be scratching your head wondering, when could this happen? And an interesting time in which this can happen is if you have secondary components framing into a concrete wall. Sometimes the secondary components are stiff enough so that they start to act as outriggers to the wall, increasing the shear demand in the walls. And in a case like that, especially for older buildings that did not require design for amplified shear forces like we do now in concrete structural walls, this can be an issue, and this outrigger effect can be significant and can change the behavior of the wall from from force controlled to shear controlled. So this is another caveat that has to be checked. Now note that these are all things that can be checked in a linear model. So you can use your linear model to iterate on these things to determine what is going to be the best use of your time in building the nonlinear model. Once you've chosen to build the nonlinear model, you do still have to check deformation compatibility, and we provide recommendations on how to do so. We recommended using either a linear model or a nonlinear static model. And that's to say that you could build a subassemblage model of some secondary components or some representative subset of the secondary components and do a nonlinear static pushover on those to the maximum displacements in the nonlinear response history analyses. And we did, as the ATC 140 project, recommend that we look at the maximum, not at the mean in the response. We felt that if you wanted to look at mean response and take advantage of that, you should put them in with the primary components. But if you want to do this on the outside of your model, you would use the maximum response. And just as a spoiler, this is one of the things that got changed in the ASCE 41 approach. And so I recommend looking at ASCE 41 and why we had the disclaimer at the beginning of this webinar to say that what we're presenting here today, when we get to these recommended revisions, sometimes is not the exact recommendations that were presented in ASCE 4123 and approved by the Standards Committee. As we move on to another very interesting challenge that came about in discussions of what do we want to talk about in terms of updating the nonlinear analysis provisions. So I think most people are familiar with Table 6.1 in ASCE 4117 and earlier editions that tell you what level of knowledge you need to have in order to do specific analysis procedures. And what you find is that if you want to do a nonlinear response history analysis or a nonlinear static pushover, you need to have usual or comprehensive level of knowledge, which means you're doing material testing. And as I'm sure many of you who've created material testing and condition assessment programs know, material testing can be very disruptive and very expensive. Now, there was language in ASCE 41 that said you could defer the testing to some later time when you're validating and use that to validate your analyses, but there's risks associated with that. If you go through your entire design, assuming a set of material strengths, and then you do your testing during construction, and you find that things tested wrong, you're going to have major changes. So what we thought about was, when does it matter and how significant can material testing be and understand knowledge of the material strength be? So again, we went to our archetype models and we started doing Monte Carlo simulations, looking at strength and stiffness. And again, going back to this concept of modeling with mean material properties, or if we were to model with, say, upper and lower bound representations of the material properties, could we get a good swath of response of the building and at least a statistically valid response to the building so that we could say, I will choose not to do material testing, but my penalty for choosing not to do material testing in order to still maintain a similar level of reliability is I will run multiple nonlinear response history models with one model with all upper bound material properties and another with lower bound estimates of the material properties so that we could get a sense for how important material properties are. So we're allowing, with the exception of unreinforced masonry, because of how sensitive that is to material property, we recommended that people be able to do nonlinear response history using upper and lower bound representations of the material strengths in developing your modeling parameters and acceptance criteria. And then looking at the envelope of responses between the upper bound and lower bound models, and in some cases, maybe needing to mix upper and lower bounds, but doing so as a way to say if you can potentially spend a fraction of what you would spend on material testing doing additional analyses to produce a retrofit with similar reliability. And then we added commentary to discuss this more. And another thing that was pointed out is that what this also gives you as the design professional the ability to do is to then decide where you want to pinpoint your material testing. Because now that you have the ability to bound material properties in your analyses, it would allow you to, for example, in a concrete structural wall building, say, I'm going to do material testing on the concrete walls, but I am not going to do material testing on the columns, the slabs, and I'm just going to focus on the walls because that's where the variability in material strength is going to have a significant change in the analysis response of the building. And then to another topic of consternation for a lot of analysts doing nonlinear response history analyses is accidental torsion. So right now, ASCE 41 requires you to run 4 nonlinear response history models with the center of mass shifted 5% in each orthogonal direction. There's language in there that talks about being able to develop factors that you can use to amplify your deformations in a model that does not have an accidental torsion mass offset. But our experience in hearing from some of our regulatory professionals or colleagues who do a lot of peer review is that while that concept is a great idea in concept, how to get to establish those factors would need a lot more text and standards direction than was provided in the standard. So we started discussing, why do we need accidental torsion in the first place? I mean, in today, we've come so far from running, planar hand calcs and distributing forces to planar frames or walls based on a hand rigid diaphragm analyses. So going back to a significant literature review and trying to understand why we need accidental torsion. So obviously the first thing is, if you have a building with a concentric center of mass and center of rigidity, but no torsional response, you run the risk of having a building that would show artificially good performance when in actuality, any little bit of twisting would have caused the building to collapse. And why is this important? Well, buildings twist. There are your estimate of your center of mass and center of rigidity may not be completely accurate, and what you model in what the model only knows what you model. And so if the real building center of mass or center of rigidity is different than the model thinks, there may be twisting that the model's not capturing. That can come from a non-uniform mass on the floor or openings that are not being modeled. It could be from varied material properties or differences in member sizes due to construction tolerances. And especially as you start taking out the stiffness of the secondary components. In addition, especially for buildings with long plan areas, the ground motions can be out of phase with on each side of the building, leading to a rotational component of the ground motion records, which is not we do not input. We don't get rotational motion in addition to the X and Y or the two horizontal components and sometimes the vertical component. So there's reason to make sure that you have some way to have your building twist in the analytical model to make sure bad things don't happen. So this is just some examples of buildings where you have high torsional resistance. So it's very unlikely that uncaptured twisting is going to cause a significant change in response of this building. Or a building that has a lot of twisting inherent in the building. We don't necessarily have to worry about making that building twist. It's this building here that has maybe strong resistance in the orthogonal directions, but has virtually no twisting resistance. So we provided some recommendations for how we could change this. And we separated the linear and nonlinear provisions so that there's clarity, and said that if your building has a torsional strength irregularity, you need to consider accidental torsion, because this is a building that if it does twist and one side of the building experiences yielding, the whole response to the building is going to change significantly. So we want to make sure we're properly capturing any sources of twisting that we didn't explicitly model. But you only need to do that in the direction where the irregularity exists. So instead of having to run 4 different iterations of mass offset, you now only have to run 1 iteration of mass offset. You may exclude accidental torsion if the eta factor is low. The eta factor is a representation of the twist of the building in a linear model when accidental torsion is applied. And that's going back to saying that when you have a building like the one in the upper left, which has a lot of torsional resistance, any unforeseen twisting will probably be accommodated by the building and all the well-distributed lateral force resisting components. You can also exclude accidental torsion if there's already significant twisting in the building, because the feeling was sometimes putting in, and especially when you're doing it via mass offset, you could be adding more twisting than the building would undergo in reality. For the nonlinear dynamic procedure, like I said, you just have to do it in the critical offset directions, not all 4 directions. At most, you're going to be doing it in 2 directions. In a lot of cases, you'll be doing it in 0 directions now. But one change also we had is that we recommended is you do need to consider accidental torsion for all hazard intensities. ASCE 4117 had a comment in there that allowed you to ignore accidental torsion if you were doing a BSE 1 and BSE 2 check. And why the committee felt that this was important to add back in considering accidental torsion is in the case of a BSE 1E or 1N performance level, you're targeting being immediate occupancy or damage control, and now those having dramatically different acceptance criteria than, say, collapse prevention. And so for those buildings, we wanted to make sure that you captured the twisting and how that might affect the immediate occupancy or damage control performance level. And then moving on to the final change that we recommended in the standard was damping. So damping can matter in analyses. What you put in as your inherent damping, and that's all the uncapped, all the damping in the structure that's not taken out by hysteretic damping or supplemental energy dissipation devices. And you know, if you change your damping from 2 to 5%, it can make a difference in the response of the structure. And so we went and we look at this and find that inherent damping is actually a highly variable phenomena. But there is some trend lines, and there's more references in the Peer Tall Building Initiative report on the relationship of inherent damping to the height of the buildings. And so we chose to adopt this equation that you see on the right, therefore allowing equivalent viscous damping ratios higher than 2% for shorter buildings. We also put in some commentary about spurious damping forces, and to make sure that you check for these things. And these can be consequences of the constitutive models and the way in which your analytical, you know, your program solves the stiffness matrix, specifically how it considers damping and whether it's putting in fictitious forces in your building. And this can also be a real concern as you start getting into explicit foundation damping modeling in soils with heavy soil structure interaction. So we chose, as we said, we adopted the peer TBI relationship. We also provided some good direction on and very good commentary on mixing modal and Rayleigh damping. We put a floor. Your damping doesn't need to go lower than 2.5% for life safety through collapse prevention. However, for tall buildings that are being held to damage control or immediate occupancy performance level, you may need to use or you may need to limit the viscous damping in your analytical model to something less than 2%. So that wrapped up all the changes that we recommended. And as any research project or any applied research project goes, we wouldn't conclude the project without recommendations for more study and more work. And so just to talk about, because some of these things are being picked up by the current ATC 140 project. Probably the biggest one is the right break for existing buildings. And when we say that, what we mean is what are the right performance objectives for existing buildings, specifically as we define the basic performance objective for existing buildings. And so we're spending a lot of time looking into that. There's also recommendations that we need to do more to study how to provide modeling parameters in quadrants 2 and 4. So those where the hysteretic shape really matters. And then also, there's a lot of discussion on the valid range of modeling and what for deformation controlled actions and what that can be. So we recommended that future studies be done on these 3 topics. And so that brings me to the end of the webinar. I want to thank you again for all the time you took, and I'm eager to hear the questions that have been posed, and hopefully I can answer some of them.
Thank you, Bob. We appreciate the good presentation. I've collected a number of questions that I'll pose to you. We've got maybe about 15 minutes that we can spend on questions. I'll start with a couple of general questions. Will the new FEMA P-2208 recommendations be restricted to performance-based design?
The recommendations in FEMA P-2208 affect the ASCE 41 standard. So the use of the ASCE 41 standard is certainly done in performance-based designs, but it is also not restricted to performance-based designs. The International Existing Building Code provides ASCE 41 as an option for their various compliance tracks when you trigger retrofits to either full code or reduced code compliance. So It's certainly intended for performance-based design, but can be used in code-triggered environs also.
Okay, thank you. Another general analysis question, is a 3D model required or is 2D modeling permitted?
So ASCE 41, and forgive me if I can't remember which edition, did eliminate the use of 2D models for nonlinear response history analyses, and I believe also nonlinear static pushovers.
Okay, thank you. A few questions about the modeling parameters and acceptance criteria that you discussed. When you were discussing the loading protocol on slide 15, the question is the collapse protocol still quasi-static?
I think most protocols are quasi-static in the lab because they're to push to a thing and then to turn around and pull back. The difference between the loading protocols is with a fully reverse cyclic protocol, you're going back and forth in the same amplitude. Whereas these collapse consistent or other alternate modeling parameters have you maybe pushing in a bias where you're pushing more aggressively in one direction and then you're not pulling back to 0 or beyond 0 and then going back and forth. But they are, again, as dynamic as you can do in a research laboratory, which I think is really quasi-static.
Yes, okay, thank you. You mentioned the introduction of point F on the backbone curve. Do you expect that will lead to more economical designs?
The hope is that it will, because what the intent of creating this point F, and I'll attempt to jump to the slide on point F right now, is that it will allow the building to have either less retrofit or remain or show that the building in its current position can meet the collapse prevention performance level. So this goes back to the concept of trying to better understand at what earthquake intensity the building truly does meet or not meet the collapse prevention performance criteria.
Okay, thank you. We've got a couple of related questions on fiber models. The first question is, can you give some examples of how a fiber model should be calibrated?
There's some discussion in the commentary, but it really points you back to the ATC 114 series of reports. But in simple terms, what it does say is you may need to build a sub-assemblage model and or either build a sub-assemblage model and recreate the test if you're trying to match test data, or at a minimum, pull a hysteretic curve from your fiber model that matches what you would use if you were to have done a lump plasticity model, and overlay the fiber model against the backbone curve and make sure that the fiber model is not exceeding the backbone curve or dramatically lower than the backbone curve.
Okay, thank you. On to critical and ordinary actions. The question, why is the load factor for ordinary force-controlled behavior not between the values used for critical and non-critical?
That was a judgment decision of the standards committee. There was no statistical basis for that. In fact, the only statistical basis was for the critical load factor, which was how much you had to separate the mean demand from the lower bound capacity to achieve a 90% reliability.
Okay, thank you. When you're talking about force-controlled actions, on slide 36, you compare two analyses. Did the connection fracture occur before or after yielding? And did the other brace buckle or not? So what's kind of the order of response in these analyses?
We varied this. The extremes I'm showing on the right is where the connection fractured before buckling or yielding occurred. Then it's not as pronounced a difference between the model with no explicit hinge fracture if you buckle but don't tend to have, if your connection is strong enough to allow the braces to buckle but the tension brace to not fracture.
Okay, thank you. In the same force-controlled actions, you talked about overstressing a member. Are you referring to demands going beyond yield strength of the member at any time, or is it member strength considered as yield capacity times some overstrength and ductility factor?
What we're talking about is putting a strength section or having some way to check what the force would be at the connection in each of your 11 records, and comparing that. And it is presumed that your deformation controlled elements have strain hardening and and median properties in them, so they're producing some sort of expected demand, and then you compare that against the expected capacity for this envelope check or unacceptable response check.
Okay. Onto the unacceptable response drift limit. Is the 6% drift ratio limit based on MCE ground motion scale to the ASCE spectrum?
It is based on whatever seismic hazard parameter you are looking to do for your evaluation. It is a unacceptable response specific to the seismic hazard intensity that you're inputting into your model. So if you are doing a BPON, where one of your things is checking collapse prevention at the MCE sub R, then what you asked would be the case. But it's also an unacceptable response for the BPOE, where your ground motions would be selected and scaled to the 975-year return period spectra.
Okay, thank you. Let's see. So then on to accidental torsion. I'll shorten the question. How is introducing accidental torsion in a 3D dynamic finite element analysis feasible?
So what we have done is artificially raised and lowered the mass over the plan that we assign to the nodes or to the elements in order to produce to have the same amount of mass on the floor, but to have a center of mass that has been shifted the appropriate percentage from the center of mass if we uniformly distributed or distribute our loads as we believe they are distributed over the floor.
Okay, thank you. In a few cases early on and then later, you talked about some Monte Carlo simulations. The question is, what does the median of the Monte Carlo simulation represent? Is that associated with some sort of probability of failure?
The median of the Monte Carlo simulation is simply the median response of the 1,000 runs we did. So if we go to the story drift parameter here, the median is simply the median of all of the, like I said, we ran 1,000 different runs and we took the median value of the parameter at each for each run. Or, I mean, sorry, for the simulation at each story, and then created that drift profile.
Okay. I have sort of a philosophical question, and I'll shorten it again, but
Sure.
we've got introducing point F, so we can look at actual collapse, and we've got secondary members. Are you concerned that sharpening our pencil so much on the capacity side that the demand side could be unpredictable and we might not be happy with the answers?
So I think that's one of the reasons that we run 11 records and that we have the unacceptable response checks now, in addition to just looking at the median. So as I said, one of the things that you are held to as an unacceptable response is the valid range of modeling. And so what we say in the standard, and I apologize for not being clear on this, is that if you know what point F is, that is your valid range of modeling. All 11 records have to keep the response within point F. So while there could be some changes in the ground motion hazard, we're hoping that by using 11 records, you've properly captured the statistical distribution of the ground shaking.
Okay, very good. Let's see, I think I have one more here. The drift limit of 6%, does that apply to all structure types, steel and concrete, for
Yes.
instance? Okay. And so maybe a question for me, is there any guidance given for methods to investigate that limit or extend that limit?
This is where the change in ASCE 4123 came. There was some more commentary given and an explicit qualifier added to the standards text saying that if you can justify stability and model performance at greater than 6%, that is not an unacceptable response.
Okay. Very good. So I'm going to close with a couple of housekeeping items. Thank you, Bob, for your great presentation, by the way. So for those of you who are eager to receive your PDH certificate, please note that they're provided for those who registered and participated in the live webinar, not the recording. You can expect your certificate within the next 4 weeks. Due to the large volume of participants, please be understanding that we can't make exceptions to our PDH policy. If you have questions that you have not yet submitted, please type them now into the Q&A window in the Zoom control panel, and we will try to provide answers to as many as possible by email after the webinar. And some final words. When you click the survey link that pops up, please click the survey link that pops up when you leave. We especially appreciate your input on topics that you'd like to see covered in future FEMA NEHRP webinars. This is how we plan our webinar program. And lastly, expect a follow-up email in the coming days with links to the recording, the handouts, and the survey. So on behalf of FEMA and the Applied Technology Council, I'd like to thank Christina and Bob for this presentation, and thank you to everyone for joining us today. This concludes the webinar.
Thank you all again.